Hey there, awesome physics students. Let's talk about equipotential lines again. They're just so useful, and there's a few more things I want to say about them. Let's go back to our parallel plate example. So we have a plate here that's oriented like this, and it's held at a potential of 8 volts, and a plate at the bottom with negative charge on it held at a potential of 0 volts. But instead of just the plain vanilla scenario here, I want to put a conductive tube inside this. So the conductive tube looks like this. It has an outer surface and an inner surface. And we talked about this before and what happens with the electric field when you put a conductive tube in here. And the electric field then, when you put that in there, it looks like this on the outside here. And then when it comes and interacts here, it's going to meet the surface because in a perpendicular fashion, because the electric field on the surface of a conductor is going to be perpendicular to the surface. And we said this happens because this distortion of the electric field occurs because the positive charges will be attracted, they'll feel a force down and be attracted to the negative charges here, and the negative charges inside the conductor, those are the free ones that are always there, those negative ones will be attracted to the top here. And we said that the electric field inside the conductor is going to be equal to 0, right? Because this conductor produces an electric field up that opposes the outside electric field from the parallel plates, and the two will add up inside and give you 0. Well, we want to talk about what do the equipotential lines for this scenario look like. Well, equipotential lines need to be perpendicular to the electric field lines. So if you're really close to the plate, it's no problem. It's the same as before. But as you get, let's say you come up here, you've got to make it perpendicular to this, and it's got to swing around and be perpendicular like that. And same with this. If I make this one, I'll cut this one a little closer. So it's got to be up like that and then down like that. And as you get closer and closer, these equipotential lines are going to sort of bunch together like this. And what about the equipotential line in the middle? Well, that comes right through the middle, and it's going to meet this conductive surface. Now remember that the electric field for the conductive surface has to be perpendicular to the surface. But equipotential lines are also perpendicular to the electric field lines. So this tells you that the conductive surface must be an equipotential line. And if this is true, then this whole surface must be at a potential of 4 volts if it's smack dab in the middle, assuming that. So that means that this whole surface is at a potential of 4 volts. That's 4 volts here, 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 here. Everywhere on that conductive surface is 4 volts. Now let's see if this makes sense. If that's 4 volts all around, then there's 4 volts inside of the surface as well. Now, how can that be? The electric field in here is 0, but the potential is not 0. Well, remember the connection between electric potential and electric field. That electric field is the change in voltage over the position. We're telling you, how does the voltage change if I move positions a little bit? Well, if I move from here to here, the position has changed, but the voltage has not. That would give me a change in voltage of 4 minus 4, which is 0. Therefore, the electric field in here should be 0. It's an equipotential surface. It's flat. There's no gradient. There's no change in the potential. There's no downhill to speak of. And so, yes, that does make sense. Now, does it also make sense that the electric field lines, excuse me, are bunching up here? What does that tell you about the electric field right around here as you get closer to the surface right here? Well, the electric field right here must be getting stronger and stronger. It's pretty strong here versus over here. Well, why would that be? Well, think about what's happened with the charge. You've induced charges here, and so the charges have kind of bunched up down here, and so there's more charges here, and so the electric field right there is going to be a bit stronger, and that's what's needed to distort this electric field to accommodate this equipotential surface. All right, so our main ideas here still hold, right? The electric field lines are perpendicular to the equipotential lines, and the electric field tells you how the voltage changes as you change position. All of that stuff is still true.